We have spent around 8 videos building up to this moment. We understand probability and neural networks. We understand loss and gradient descent. We understand attention and why it's such a breakthrough. Now it's time to pull all those pieces together into one complete machine. That is this video. The transformer architecture. This is the actual design behind GPT, ChatGPT, Cloud AI, and Gemini. Not hype, not marketing, but real engineering that makes these systems work. At the end of this video, you will understand the complete blueprint when someone mentions transformer or GPT architecture. You will know exactly what they are talking about, every component, every connection, and every design choice. So here's our question for today. How do we combine attention, learning, and probability into one working language model? That's what the transformer architecture does. And that's what we are going to understand. Before we look at the details, let's understand how the transformer is actually doing, what transformer is actually doing at high level. The whole thing boils down to 3 main operations, and they are happening in loop. Step 1 is understanding the relationship. This is where attention comes in. Each word looks at every other word and figure out which one are relevant. Step 2 is processing that information. This is where neural network layer transforms, refines the understanding. Step 3 is predicting the next token. This is where probability comes in, outputting a distribution over all possible next word. And those 3 steps don't just happen once. They repeat over and over through dozens or even hundreds of layers, each time refining the representation further. Here's a way to think about it. Imagine a publishing house and its workflow. Editor reviews the content and decides what's important. That is attention. Writer refines, transforms the text. That's neural layer. Publisher releases the final version, and that's the output prediction. Stack these steps, repeat them many times, and you get a transformer. Now let's look at what's actually inside each transformer block. Every block contains 4 main pieces working together. First is multi-head attention. This is where words look at other words. The multi-head part means we run several attention mechanisms in parallel, each one focusing on different type of relationships. Some head might track grammar, others might track meaning, others might track long-range connection. Second is feed-forward network. This is standard neural network that process each word position independently. This is where the model thinks about what it learned from attention. Third is residual connection. These are shortcut paths that add the input directly to output. This sounds simple, but it is critical. Without residual, information would get lost as it flows through dozens of layers. Fourth is, the final layer normalization. This keeps all the values in a stable range during training. Without normalization, training becomes unstable and fails completely. These 4 components form one block, and the model stacked many of these blocks. For example, GPT has 96 layers, each layer built on the previous one, with early layers handling simple patterns like grammar and deeper layers handling abstract patterns like reasoning and meaning. Now let's see how it's all fit together in one visual. Look at the architecture diagram on the left, At the very top, we have input layer. This is where token get converted into vector and positional information get added. We'll talk more about positions in a moment. Then we have the main block um, that repeats itself maybe n times. Inside the block, first comes multi-head attention plus add and normalize. Then the output flows to feed forward network, again with add and normalize. The add is the residual connection and the normalize is layer normalization. This whole block repeats many times, 12 times for smaller models, 96 times for models like GPT-3. At the bottom, we have the output layer. This takes the final representation and produce probabilities over all possible next token using softmax. Think of it like an assembly line. Each layer reviews the previous output, refines understanding, and passes an improved version forward. Like a car moving through a factory, each station add more detail and polish until you get the finished product. Here's something we haven't addressed yet. Attention by itself ignores word order. When attention computes the relationship between words, it doesn't care which word comes first, right? But word order matters a lot. Look at these two sentences. Dog bites man and man bites dog. Same three words, but completely different meaning. If the model ignores order, it would treat these as identical, and that's a problem. The solution is positional encoding. We add information about each token's position directly into its vector, vector representation. So the token right at position 0 has a different number added than the token cat at position 1. Look at this visualization. Each word has a position encoded as a small vector, right? That gets added to the word's embedding. These position vectors follow a specific pattern using sine cosine functions, which helps the model understand about absolute position and relative distance between the words. Here's a mental model for you to sort of keep it in mind. Musical notes alone don't make music, right? Their position in time matters. A C note played on the first beat means something different than a C note on the last beat. Position encoding is like adding rhythm to the words. It tells the model where each token sits in the sequence. So dog bites man and man bites dog become clearly different. Now here's something that confuses a lot of people. There's actually two major type of transformers designed for different tasks. On left we have encoders. Encoders see the input at once with attention flowing in both directions. This makes them great for understanding tasks, right? For example, things like classifications, sentiment analysis, or extracting information. BERT is the famous example of an encoder. On the right, we have decode. Decoder generate text one token at a time, and they can only see past tokens, not the future ones. This makes them perfect for generation tasks. GPT, ChatGPT, and Cloud are all decoder only transformer. So why do ChatGPT and Cloud use decoder only architecture? Because their job is text generation. When you are generating text, you can only see what you have already written. Future word doesn't exist yet. The decoder mask attention enforces this naturally. Each position can only attend to earlier position, which matches exactly how text generation works. Now let's trace through how a transformer actually learns. This connects everything we learned in earlier videos. Okay, look at this animation. Step 1 uh, is tokenize. Break the text into pieces. Step 2 is add position. Encode where each word, right, sits. Step 3 is attention. Let words look at each word. Step 4 is feed forward. Process each position with neural layer. Step 5 is predict. Output probability distribution over vocabulary. Step 6 is loss. Compare prediction to actual next word. Step 7 is update. That is adjust weights using gradient descent. Then we go back to step 1 with new text and repeat. The entire loop repeat billions of times across trillions of word token. Each pass adjusts the weight slightly, and over time the model gets better at prediction. This is exactly what we covered in video related to gradient descent. But now you can see how it fits into the complete architecture. Here's something remarkable about transformer. They are not just good, they get predictably better as you make them bigger. This wasn't true for earlier architecture. There are 4 key properties that enable scaling. First, parallel processing. Attention computes all words relationship at once, not one at a time. So you can use hundreds of GPU effectively. Second, this is like long context. Any word can attain to any other word regardless of the distance. Third, stable gradient. The residual connection and layer normalization keep training stable even with 100 layers. Fourth, the architecture is data hungry. It can absorb massive data set effectively without plateauing. Research has shown consistent scaling laws. More data, more parameter, more compute. They all predictably improve the performance, right? More data, more parameters, and more compute actually go ahead and improve the performance. That's a law, scaling law. Double compute get consistent improvement. This formula is why companies race to build bigger models, because with transformer, bigger reliably means better. And here's the key point. Without the transformer architecture, GPT wouldn't exist. ChatGPT wouldn't exist. The entire modern AI boom is built on this one architecture. The transformer are the first architecture where scaling actually works reliably. Now that you understand how transformer works, let's be honest about what they can do and what they cannot. This matters for using these tools wisely. First, transformer don't have a world model. They learn patterns in text, but they don't understand what the physical world actually works. They can describe how gravity works because they have read about it, but they have no intuition for physics. Second, they are they are there's no grounding. Words are statistical pattern and connected to real things. The model has no connection between the word apple and an actual apple you can eat. Third, everything is data dependent. The model only knows what was in the training data. Errors in data becomes errors in output. Gap in data becomes gap in knowledge. The honest assessment is this: transformers simulate intelligence very convincingly. The pattern they learn are quite advanced and quite advanced enough to fool us most of the time, but simulation is not same as understanding. Knowing this helps us use these tools effectively. You understand both what they are capable of and what they fall short of. Alright, let's make sure everything comes together. If this video worked, You should be able to say one sentence and understand every word of it. A transformer combines attention, neural processing, and positional information in stacked layers to model relationship in language and predict the next token. Take a moment with this sentence. So first, let's try to understand attention in this. That word looking at that's word tells you that all the words looking at other words, right? A word look at other words. Neural processing, that's the feed layer, feed forward layer, right? Positional information is that encoding where each token sits. Stacked layer, that's repeating the block many times. Model relationships, that's what attention captures. Predict the next tokens, that's the output. If that sentence sounds simple, simple to you now, and not impressive or complicated, but just obvious, then you truly understand the architecture. That's the goal, making something that seemed intimidating feel natural and clear. So we've gone from what is LLM to understanding complete transformer architecture, but there is a lot more to come, and we'll see these topics one by one in coming lectures. If this series has helped you understand how AI actually work, share it with someone who is still confused by the buzzwords. You have now the knowledge that most people don't, and use it well.